first. When we're done with that, we'll be moving to chemistry, and then we'll be doing biology last. So let's see how far we'll be able to go with each of the questions. I'm going to be covering questions, covering all the aspects of physics, chemistry, biology, and we'll be expanding into other areas that are very relevant to the forthcoming exams you will be writing. So let's go to physics first. And as the class is going on, if there's any area you have questions or maybe you don't understand, feel free to ask. And I know in the last class, some of you were actually complaining about your inability to get some of the questions being projected. If you want the questions after the class, you can just pay attention. The soft copies are with us, so you can easily get the soft copies free of charge. So if you need the soft copy of all the questions, either the one we've done before and maybe the answers to both the questions and the soft copies of all the questions, the answers to them, of everything we've been doing since we started on Friday, they are available. So don't bother about being unable to copy the questions from the slide. The copies are available for you to freely ask. That is if you want them. So let's get started by looking at the very first question on the slide. And it says, in a thermoflask, the cork stopper minimizes its loss by dash. Now, we know that a thermoflask, also called a vacuum flask, is a particular device that is used to store liquid and substances and to minimize its loss or gain by various means. And we know that its loss usually occurs in three ways: by radiation, by conduction, and of course by convection. Now, two of these processes through which heat are lost require material medium, and the two of them are conduction and convection. Conduction usually takes place in solid. Convection usually takes place in fluid. Fluid comprises gases and liquid. So both conduction and convection require material medium, whereas the third one, which is radiation, does not require any material medium. So in a thermoflask is made in such a way that all these loss of heat by these three processes are greatly minimized. For example, the cork stopper, the question is asking us, is at the top, it's like a lid that closes that particular vacuum or thermoflask. So the cork stopper prevents or minimizes its loss by three means. One, by conduction. Don't forget, the cork stopper is actually made of wood, and we know that wood is not a good conductor of heat. Not only that, because the cork stopper is actually plugging and preventing whatever fluid that is present in the thermoflask from escaping into the atmosphere, the cork stopper also minimizes its loss by evaporation of liquid stored in it. And not only that, it minimizes its loss by convection. So if you put the three of them together and we take a look at the option, we can see that the correct answer for this would be option C. So the cork stopper minimizes its loss by conduction, by evaporation, and by convection. So what about the other parts of a vacuum flask? Now, the vacuum, because a vacuum flask has two walls, the outside wall and the internal wall. There's a vacuum in between it. The vacuum in between the walls in a thermoflask or in a vacuum flask minimizes its loss by both conduction and convection. And then the outside of the walls are actually silvered, covered with silver. That's what that means. And the silvery cover of the walls minimizes its loss by radiation. Not only that, we have the cork support. Now we're having two corks. We're having a cork on top, which is the cork stopper, that minimizes its loss by conduction, by convection, and of course by evaporation. For the cork support is the support on which the thermoflask is put is also made up of wood. So the cork support minimizes heat loss only by what? By conduction. So please take note of those four things. The cork stopper, that's the one on top, minimizes heat loss by conduction, by evaporation, and by convection. The vacuum between the two walls minimizes heat loss by both conduction and convection. And the silvered walls on those two walls minimizes heat loss by radiation. And finally, the cork stopper, that the cork support rather, on which the thermoflask is put, minimizes heat loss by only conduction. So the correct answer for this, obviously, option C. Let's go to the next slide. Okay, number 2. Which of the following devices stores and transfers charges? We have a capacitor. A capacitor is a device that stores charges, among other things. We spoke about capacitors on Friday, didn't we? A capacitor can store charge. A capacitor can store energy. A capacitor can be used in tuning radios. A capacitor does a whole lot of things. But what a capacitor cannot do is a capacitor cannot transfer charges. It can only store them. So capacitor cannot be the correct answer here. If you look at option B, which is the correct answer, an electrophorus is a device that does three major. An electrophorus not only stores charge, it also aids in transferring the charge. And the third one is an electrophorus also aids in producing charges by electrostatic induction. So the three major functions or uses of an electrophorus are: number 1, an electrophorus can produce charge by electrostatic induction. Number 2, an electrophorus can store charges, just like a capacitor can store charge. And number 3, an electrophorus can also transfer the charge from one place to another. And if you look at option C is gold leaf electroscope. It's one of the most important devices in electrostatics in physics. It does 4 major things. Gold leaf electroscope helps to identify the presence of charge on a body. So a gold leaf electroscope can tell us if a particular object is carrying a charge or not. Not only that, a gold leaf electroscope can tell us the type of charge a particular object is carrying. So you can use gold leaf electroscope to test for the type of charge. Is it a positive charge? Is it a negative charge? Not only that, a gold leaf electroscope can be used to determine the amount of charge on an object. Is it carrying a high quantity of charge or a small amount of charge? And the fourth one, gold leaf electroscope can also be used to distinguish between conductors and insulators. Once again, there are 4 things that gold leaf electroscope does. Number 1, it is used in detecting the presence of charge on a body. Number 2, it is used in detecting the type of charge on a body, be it positive charge or negative charge. Number 3, it is used to determine the quantity, how much of a charge is present on a body. And the fourth one, the last one, gold leaf electroscope is also used to distinguish between conductors and non-conductors. Now, I was telling you that we can use gold leaf electroscope to determine the type of charge on a body. Either it is positively charged or negatively charged. How does it do that? If you have a gold leaf electroscope and you know the charge on that gold leaf electroscope, let's say the electroscope is positively charged. Now, if you bring another positively charged near the cap, what happens? That particular gold leaf diverges, all right? It diverges by increasing the distance between the rod and the gold leaf. The divergence of the gold leaf will increase because like charges always repel. But if the gold leaf electroscope is positively charged and you bring a negatively charged substance which is opposite to the top of the brass, what happens? The divergence decreases, the gold leaf gradually collapses. Now, if you bring an uncharged body near a gold leaf electroscope, the same thing that happens when you bring an opposite charge near it happens as well. So which means if a gold leaf electroscope is positively charged and you bring an uncharged body near the car, the divergence will also decrease. It's as if you are bringing an opposite charge near it. So the correct answer for this will be option C. If you are wondering what the function of proof plane is, proof plane is a device used only for doing what? For transferring charges. Well, the question is asking us which device not only stores charges but also transfers it, and that is electrophorus. Electrophorus produces charges by electrostatic induction. Electrophorus stores charges. Electrophorus also transfers charges. But proof plane cannot store charges. It cannot produce charge. It can only transfer charge. So the correct answer for this is option B. Let's go to the next slide. Option B. So that's for that. The next slide. It says a ball is projected with a velocity of 10 meters per second from the ground level at an angle of 75 degrees to the vertical, where I have to calculate the horizontal distance covered by it. And we are supposed to take the acceleration due to gravity to be 10 meters per second squared. It is obvious this topic is on what? On projectile. So if we look at the board and we have our axis like this, a projectile always moves like this. The path that is followed by a projectile, we call it a trajectory, and the shape of a trajectory is always a parabola, and this is the angle of projection that we need, and the horizontal distance covered by it, we refer to it as the range. So this is the range, the horizontal distance covered by a body during projectile. Now, we are being given, because we need to be careful here, we are being given the initial velocity to be 10 meters per second. But if you look at our theta here should be the angle to the horizontal, not the angle to the vertical. And if you look at the board, you will notice that this is the angle to the vertical, which means the angle between this to this is 75 degrees. But the angle we actually need is the angle from here to the horizontal. But we know that everything from here to this place is what? That's 90 degrees. So if from here to here 75 degrees, to get this one, what do? We just subtract the 75 degrees from 90 degrees. What would that give us? 15 degrees. So which means our theta now is going to be 15 degrees. And then we know our G to be 10 meters per second squared. Now we need to calculate the range. We know the formula for calculating range. Range is calculated by U squared, then sine 2 theta all over the G. Now, so if you substitute the various parameters we are given, the initial speed is 10, scale of 10 is 100, then times sine of 2 times theta. 2 times 15 will give us sine 30 degrees all over the G. That's 10. So this becomes 100 times sine of 30 is 0.5 or half divided by 10. 0 here, 0 here. and 10 times half will give us 5 meters. So our range or the horizontal distance will be 5 meters, which is obviously option A. Now, before I move on to the next question, you must know that there are other questions you could be asked in projectile, apart from the fact that they can ask you theoretical questions like asking you that the path that a projectile follows is called what? We refer to it as a trajectory. Not only that, the shape of a trajectory can also be asked. It is always a parabola, or you can say that a projectile path is always parabolic in nature. Not only that, this range, they can ask you at what angle must an object be thrown or projected in order to achieve maximum range that is going to be at angle 45 degrees, because range is going to be maximum when the value of sine 2 theta is equal to 1. And the only time that the angle of sine 2 theta here can be equal to 1 is if 2 times this theta will be equal to 90 degrees. And we know what we can multiply by 2 to give us 90 degrees is 45 degrees. So for an object to attain maximum range, such an object must be thrown or projected at an angle of 45 degrees. However, for an object to be thrown to achieve maximum height, we're talking about height now, no longer range, such an object must be thrown vertically upward, which means that the angle of projection should be what? 90 degrees. If this is the ground surface, for an object to achieve maximum height, it must be projected vertically upward like this, which means the angle to the horizontal will now be 90 degrees. Know the difference between the two of them. For an object to be thrown or projected to achieve maximum range, it must be thrown at an angle that is equal to 45 degrees. But for an object to be thrown to achieve maximum height, it should be thrown at an angle of 90 degrees. So let's take note of that. Another area that you have to be careful about are questions involving time of flight. The time of flight has the formula like you already know. C is equal to 2u sine 2 theta over d here, where u is the initial velocity with which it was thrown, theta is the angle at which it is projected to the horizontal. But where I'm going is this. At times, the question might be asking you to calculate the time taken to reach maximum height. A lot of students confuse the time of flight with time taken to reach maximum height. They are not the same at all. Time of flight is the time it takes from here to move to get to the maximum height here and to also come down to the same horizontal ground from which it is projected. The time to reach maximum height is half of the total time of flight, which means that if the total time of flight is 10 seconds, the time to reach maximum height is going to be half of that particular 10, which is 5 seconds. Or instead of asking you to calculate the time of flight, you guys could be asked to calculate the time spent in air. That's another name. Time spent in air, because when it is projected, now when it begins to move, now it's now in the air until it comes down. So time of flight is also called the time taken or the time spent in air. But take note, the time taken to reach maximum height is only half of the entire time of flight. I hope that is understood. Let's go to the next slide. Okay, it says, a spring balance which is suspended from the roof of a lift carries a mass of 20 kilograms at its free end. If the lift falls freely, the reading on the spring balance is what? And we are given once again the acceleration due to gravity to be 10 meters per second square. Now, this is one of the common and popular questions that is usually encountered in physics, and care needs to be taken while we are doing questions like this, because the body, that particular lift, could be moving down, it could be moving up, and depending on the direction that will determine the formula that is used. If a lift is moving up, the formula to use will be this. For upward motion, T, that's the reading of the lift, minus mg, that's the product of the mass of that particular object or the man, and the acceleration of gravity is equal to ma. This is for upward movement. Now, if the lift is moving downward with a particular acceleration, the formula to use will be mg minus t is equal to ma. M is the mass of the body. G, of course, you know that is the acceleration due to gravity. The T, that is the tension or the reading in that particular lift or in the scale. And A air is the acceleration with which the body is either moving down or moving up. But if you look at this, the question says that if the lift falls freely, and by the way, when something falls, does it move up or down? It comes down, which means that here we are going to make use of this formula because it is moving down. So which means mg minus t is equal to ma. Now t air is the reading, and that's exactly what the question is asking us, the reading in the spring. And if we make this reading the same formula, we bring this one air and we take t to the other side. Now we are left with mg, when this one comes here, minus ma is equal to t. Now here, m is common, so we can factor m out. M now is equal to g minus a is equal to t. But the operative word here is the word falls freely. When something falls freely, it means that, don't forget, when something is falling, what is the force acting on it? The force of gravity. When something is falling freely, when you see that particular condition, when a body falls freely, it means that the acceleration of that particular body that is falling freely is equal to acceleration due to gravity. What that means is A is equal to G. Please take note of that. Anytime you see the word like an object falls freely, it means the acceleration of the body is equal to the acceleration due to gravity. And if you substitute that here, what do you have? Here now, there's not going to be any G here anymore. That becomes M into G minus A is equal to T. If A is equal to G, it means that this particular G here, I can substitute A into A because A is equal to G. And here, A is equal to T. You know where this is going. M now is equal to A minus A. That becomes 0 is equal to T. Even though the mass is given there to be 20 kilograms, the mass doesn't matter anymore. Because once the mass is multiplied by 0, it becomes 0. As a matter of fact, if in an exam, I would not expect you to waste time doing this. I'm only doing that to be able to show you why the answer will be 0 Newton. Once you must have seen that the lift falls freely, I expect you to know that, oh, it is falling freely. Whenever any body or any object is falling freely under gravity, it means that the weight of that particular body is 0. In physics, we call it weightlessness. You guys know what weightlessness means. So when a body is falling freely under gravity, it appears as if it is weightless. That is why the Newton, the force acting on it, is 0. So the correct answer for that will be option C. Let's go to the next slide. Okay, which of these is not a consequence of total internal reflection of light? Now, there is a particular phenomenon in physics called total internal reflection of light. It occurs under two conditions. Before total internal reflection of light can occur, the light must be traveling from an optically denser medium to an optically less dense medium. In some questions, instead of less dense medium, they call it rarer medium, R-A-R-E-R. So for light to undergo total internal reflection, it must be traveling from a denser medium like glass to a less dense medium like air, or from a denser medium like water to a less dense medium like air, or from a denser medium like glass to a less dense medium like water. Number two condition is the angle of incidence in the denser medium must be greater than the critical angle. Once again, the angle of incidence in the denser medium must be greater than the critical angle. So these are the two conditions for light to be able to undergo total internal reflection. Once again, the light must be traveling from an optically denser medium like glass to an optically less dense or rarer medium like air. And number two, the angle of incidence in the denser medium must be greater than the critical angle. And if you are wondering, what is critical angle? Critical angle is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is 90 degrees. So that's for that. And there are four major consequences of total internal reflection of light. They are formation of an optical illusion called mirages. Now, if a person is traveling on a very sunny and hot day on a tarred road, it is not unusual for you to see in front of you, it's as if there is a pool of water. But as the vehicle approaches it, it moves further forward. You will never get to where that particular pool of water appears to be. Why? Because it is not real. That's the meaning of optical illusion. So formation of mirages is one of the consequences of total internal reflection of light. Another consequence of total internal reflection of light is the eye view of fish. Even fish that are inside water can see what is happening above the water because light from air that goes into the water undergoes total internal reflection of light, making it easy for the fish underwater to observe what is happening above the water. The third phenomenon or consequence of total internal reflection of light is the shining nature and the brilliance of diamond. Diamond is one of the most sought after minerals. If a diamond is held in the hand and you show light on it, it dazzles, it has this brilliance because of its shining nature, because of its high refractive index. That is why it's used in making jewelry. So that particular bright and shining nature of diamond is because of total internal reflection of light in it. And the fourth consequence of total internal reflection of light is what we refer to as looming. L-O-O-M-I-N-G. So if you take a look at the options, you will see that the correct answer, which is not a consequence of total internal reflection of light, would be swimming pool appearing shallower than it really is. When a swimming pool appears shallower, all right, than it actually is, that is caused due to refraction of light. It is refraction of light that makes swimming pool to appear shallower, all right? We call it apparent depth. To appear shallower, if you stand at the edge of a swimming pool, or if not a swimming pool, you're in the house, and you have a metallic spoon in a bucket, and you pour water into such a bucket, and you look down into that particular bucket, the spoon at the bottom of the bucket appears closer to the surface than it actually is. That is due to refraction of light, not due to total internal reflection of light. It is also this refraction of light that makes an object to appear bent when you dip them in water. If you dip a straight object into water and you observe it, it's as if that, it's just like when a stick is dipped into a bucket filled with water, the stick will appear bent in nature. That bent nature is due to refraction of light. And what is refraction of light? Refraction of light is simply defined as a change in the direction of light as it travels from one medium to another. Another area where questions do come from is asking you, during refraction of light, which of the following characteristics of light wave remains unchanged? When light undergoes refraction, four things change about it, and one thing remains unchanged. When light undergoes refraction, the direction changes, the wavelength changes, the velocity changes, the intensity changes. But when light undergoes refraction, one thing that remains unchanged is the frequency. So during refraction of light, the frequency is not affected, it remains unchanged. And before I move on from this, at times questions do come from applications of total internal reflection of light. In what ways is total internal reflection of light applied in real life? Now, one of the ways in which total internal reflection of light is put to use is in optical fiber cables. They are called OFCs. That's what is used, among other things, in transmitting signals, in transmitting data. You are here now with your phone, and you can bring up your phone, you can browse, because the OFC, the optical fiber cables, can transmit data from one place to another. Not only that, you can sit here and watch football matches being played in UK, for example, without being there, you can watch it in real life as it is happening over there. That is another application of optical fiber cable. It is used in telecommunication, in transmitting signals from various parts of the world. Not only that, when a person goes to the hospital, maybe for certain tests, if a person is feeling as if something is stuck in the neck and goes to see a doctor, they can put in a particular instrument called an endoscope. Endoscope also uses this total internal reflection of light. So, total internal reflection of light is used in making optical fiber cables, which are used in telecommunications, in transmitting data, which are used in medicine, in endoscope, in observing the inside of the throat. So, I hope that is understood. Let's go to the next slide. The next slide. Okay, which of these is or are the complementary color or colors of yellow? Now, we know we have two major types of colors, don't we? We have primary colors. There are three of them. The three primary colors are blue, green, and red. An addition of the three primary colors will give us white. Once again, the three primary colors are red, blue, and green. And the addition of these three primary colors will give us white. But we also have other type of color called secondary color. How is secondary color formed? By addition of two primary colors. When two primary colors are added together, it produces a secondary color. Don't forget, the three primary colors are red, blue, green. So which means that if red and blue combines together, it's going to produce a secondary color. And the name of the secondary color, when red and blue combine together, is called magenta. So red plus blue will give us magenta. Magenta is an example of a secondary color. Not only that, if you have red and green combining together, it will give us yellow. That is another secondary color. So yellow is a secondary color made up of two primary colors, which are what and what? Red and green. And then the last but not the least of the three secondary colors are blue and green combining together. So when blue and green colors combine together, it produces a secondary color called cyan. Cyan is spelled as C-Y-A-N. Now, you know the three primary colors that we have: red, blue, and green. Now, you know the three secondary colors we have: magenta, which is made up of what? Red and blue. Yellow, which is made up of red and green. And then cyan, which is made up of blue and green. So, now, complementary colors are always a mixture of one primary color and one secondary color. Complementary colors are two colors that can combine together to give you white color. So they are asking us, what will be the complementary color of yellow? Don't forget, I told you yellow is made up of red plus green. And I told you that the three primary colors, when they are combined together, they give white color. Yellow already contains red and green. Which color is mixing that we can add together to give us white color now? Blue. So the complementary color of yellow is definitely blue. So the correct answer for that is option B. The next slide. Next slide. Okay, it says the angular magnification of an astronomical telescope in normal use is 5. If the focal length of the objective lens is 100 centimeters, the question was asking what the length of that telescope will be. Sorry for that. The question should be the length of the telescope. So the question is the angular magnification of an astronomical telescope in normal use is 5. And if the focal length of the objective lens is 100 centimeter, what is the length of the telescope? Now, we know telescope is one of the optical instruments that are used. And what do we use astronomical telescope to do? We use it in observing celestial bodies like the stars, the planets, and so on and so forth. And astronomical telescope is made up of two lenses, the objective lens and the eyepiece lens. The objective lens have a focal length denoted by f naught. That's the focal length of the objective lens. F naught for objective lens focal length. And the focal length of the eyepiece lens is denoted by this. That's the eyepiece focal length. And the angular magnification, the formula for angular magnification of an astronomical telescope is M is equal to the focal length of the objective lens divided by the focal length of the eyepiece lens. And the question is, what is the length of the telescope? The length of a telescope is the sum of the focal length of the eyepiece lens plus the focal length of the objective lens. That's how to calculate the length of a telescope. Once again, the length of a telescope, it doesn't have to be astronomical. It can be terrestrial telescope. It can be Galilean telescope. When you want to calculate the length of any telescope, it is always a sum of the focal length of the objective lens, FO, plus the focal length of the eyepiece lens, FE. Now, we already know what the focal length of the objective lens is, 100 centimeters. So, FO here is already 100 centimeters. What we need now that is yet unknown is FE. But we can easily calculate that, can't we? Because the angular magnification M is given as 5. So we can say magnification, which is M, is equal to 5, is equal to FO. That's the focal length of the objective lens. It has been given as 100 centimeter, 100 centimeter divided by FE. That is the focal length of the eyepiece lens. And if you make FE the formula, FE becomes 100 centimeters divided by, the 5 comes here, divided by 5. And that gives us what? That's going to be 20 centimeters. And like I said earlier, if you want to calculate the length of a telescope, what do? You add the FO, the focal length of the objective lens, with the FE, the focal length of the eyepiece lens. So FO is 100 centimeters. We just calculated our FE to be 20 centimeters. So what then becomes the length of the telescope? That is 100 centimeters plus 20 centimeters, and that gives us 120 centimeters. It's as simple as that. Please do take note of this formula. M, that's the angular magnification is equal to the FO, the focal length of the objective lens, divided by FE, that's the focal length of the eyepiece lens. So please take note of that. And another thing, before we move on to the next question, another question that are common and pertinent about telescope is, they can ask you, if you look at the question, it says that the telescope is in normal use. Another name for normal use is normal adjustment. They can ask you that when a telescope is in normal adjustment, the final image will be dash, and then you get various options, virtual, and so on and so forth. Whenever a telescope is in normal use or in normal adjustment, the final image will always be formed at infinity. Once again, when an astronomical telescope is in normal use or in normal adjustment, the final image will be formed at infinity. Let's take note of that. Now let's move on to the next slide. Oh, we've done it because this should have been the question for number 7. Calculate the length of the telescope. So let's go to number 9 now. Okay. So it says, a man standing between two cliffs claps his hands and hears 2 echoes after 6 seconds and 4 seconds respectively. Calculate the distance between the cliffs. And we are given the speed of sound in air to be 330 meters per second per. So let's rub this off so that we can put a diagram that can make it easier for us. So for us to understand this very well, let's do it like this. So let's say this is the first cliff, and here is the second cliff. And then this is where the man, if I put the position of the man, take a look at the question. When the man claps his hand, look at the time it takes for the 2 echoes to be added back. One took 6 seconds and the other one took 4 seconds. If you look at it, these are 2 different times. Why is it that the times are not equal? Now, the closer you are to a wall, the faster it is to get the echo back. Now, if I'm standing here to that particular wall and I clap my hand, I'm going to get the echo faster than now. I'm between this wall and that wall. I'm obviously closer to this wall, and I am more farther from that particular wall. So if I clap my hand, I am going to get the echo from this wall faster. That is it's going to take a shorter time for the echo from that particular wall to get back to me, and it's going to take a longer time for the echo from that particular wall to get here. That is the reason why the 2 times are different. So which means the man is closer to one of the walls. So if this is the man, now the distance from air to air, let's say this is x, and the distance from air to the wall air, let's make it y. And the question I'm now asking now is, what is the distance between the 2 cliffs? That is the distance from air to air. And the beauty of it is, if you're able to calculate what x is, and we are able to calculate what y is, what do we do to get the distance between the 2 walls? Just add them together. And you know the famous formula, speed of sound in air, v, is equal to 2g all over t. V is the speed of sound in air. G is the distance between a man and an obstacle, like a wall or a cliff. And then T is the time it takes for the echo to be heard back after a man must have made a sound or clap his hand. So let's calculate the distance from air to air. Since this one is x, we are going to change this formula now from v is equal to 2d all over t2. That's going to be 2x all over t. I hope you know what I'm doing here. So here we are going to make x the subject of the formula. By doing that, we are constantly applying so that we have 2x is equal to v times t. That's vt. And if you want to make any formula, we divide both sides by 2. So x now would be v. That's the speed of sound in air. 330 times the time. Please take note. This man is closer to this wall now, which means that the time is going to take is going to be shorter. It's going to be lower. So between 4 seconds and 6 seconds, it's going to take 4 seconds. So here, that's going to be 4, then divided by 2. 2 here, 1, 2 here, 2. 330 times 2 will give us 660. So here, it's going to be 660 meters. And unfortunately, if you look at the board, 660 is there. But that's not what the question is asking us. Now, let's find how far is this man now from this particular wall here. We are looking for y. So you can change this formula again to y. So that we now have v is equal to 2y all over t. And if we make y the same formula, here we'll be having 2y is equal to vt. And then dividing both sides by 2, we're having our y to be vt all over 2. V remains the same as 330 times this time around, because the distance from air to air is longer. It's going to be the longer time, which is 6 seconds. That's 6 divided by 2. 2 goes here, 1, 2 goes here, 3. And 3 times 330 will give us 990 meters. Also, it is there. But now, we know from air to air, is 60 meters. From air to the second wall is 990 meters. The distance between the two cliffs now will be 660 plus 990. What will that give us? That's 1,650. That's how to easily do it. All you need to be able to do is be able to know that the 2 times that are given are going to be allocated differently. The time, the shorter time, is going to be from where a man is closer to the wall. The longer time, 6 seconds, is going to be from a position where the man is more farther away from the wall. So it's as simple as that. Let's go to the next slide. Next slide. Okay. The torque experienced by a rotating rectangular coil between 2 permanent magnets is 0 when the coil is dash A, perpendicular to the magnetic field, and so on and so forth. You just look up. Now, in magnetism, the torque, that's the rotating force, that's the meaning of a torque. The rotating force on a particular rectangular coil is calculated by using this formula. T, that's torque, is equal to B A N I cos theta. That's the formula for calculating a torque. And if you are wondering, what does all this stand for? B, that's the magnetic flux density. It is measured in Weber per meter squared or Teslas. The A here is the area of the rectangular coil. At times, they call the coil armature. Now, the N here is the number of turns in that particular coil. At times, they call it the number of loop, L-O-O-P. And then the I here is the amount of current passing through that particular coil. And the theta here is the angle between that particular coil and the magnetic field. And for the value of T here to be equal to 0, the value of cos theta here needs to be equal to 0. And for the maximum value of cos theta is 1. And that happens when theta is either 0 degree, that's when it is parallel, or it is 360 degree. But for theta here, for the value of cos theta to be equal to 0 here, it means that theta must be 90 degrees. You can pick up a calculator and find out what is the value of cos 90 degrees. 0, right? And when cos 90 becomes 0, 0 multiplied by everything here becomes 0 as well. And when theta is 90 degrees, what does that mean? It means the coil is what? Is perpendicular to the magnetic field. So if you take a look at the option, we will see the correct answer is option A. So the torque that is acting on a rotating rectangular coil in between two permanent magnets will be 0 only when the angle between that coil and the magnetic field is 90 degrees, because the value of cos theta will be 0 only when theta is 90 degrees. Let's go to the next slide. Okay, which of these is not a component of an electric motor? First things first, what's an electric motor? An electric motor is a device that converts electrical energy into mechanical energy. It works in opposite manner with a dynamo or a generator. A generator or dynamo converts mechanical energy into electrical energy, whereas an electric motor does the exact opposite by converting electrical energy into mechanical energy. There are 4 basic parts of an electric motor. You have a permanent magnet that is housing or on the right and left side of the armature. And then you have the armature. I've told you before, armature is also called the coil. And not only that, you have the split ring commutator as well. And not only that, you have the carbon brushes. So if you take a look at the board, you will see that the correct answer here would be slip ring. Slip ring is not present in an electric motor. Rather, what is present is split ring commutator. And the function of split ring commutator is to reverse and change the direction of current. So the correct answer would be option A. The next slide. Okay, now we have 4 Roman figures here. Roman figure 1, strength of the magnetic field. Roman figure 2, speed of rotation of the coil. Roman figure 3, number of turns in the coil. Roman figure 4, area or surface area or cross-sectional area of the coil. The question now says, induced EMF produced in a dynamo. By the way, dynamo is a generator. Depends on which of the following factors. We know that the induced EMF that is produced in a generator or dynamo depends on all of them. Depends on the 4 of them. Number 1, it depends on the strength of the magnetic field. The stronger the magnetic field, the higher the amount of induced EMF. Number 2, it depends on the area of the coil. The larger the area of the coil, the more magnetic line of force it can store, and the higher the induced EMF. Number 3, it also depends on the speed of rotation of the coil in between the 2 permanent magnets. The faster it rotates, the higher the speed of rotation, the higher the magnetic field. And last but not the least, it depends on the number of turns. The higher the number of turns in that particular coil, the higher the induced EMF. So it depends on all of them. And if you take a look at the board, you will see the correct answer here would be option D. And don't forget, induced EMF is what Lenz's law was speaking about, isn't it? Induced EMF, Lenz's law and Faraday spoke about this. Lenz's law was telling us that an induced EMF always flow in such a way, an induced current always flow in such a way as to oppose the change producing it. And Lenz's law, don't forget, is an example of conservation of what? Of energy. So that's for that. Let's move on to the next slide. Okay, energy loss due to magnetic flux leakage in a transformer can be minimized by that. We know what a transformer is. A transformer is a device for stepping up and stepping down voltages. That's why we have two types of generators. We have step up transformers, and then we have step down transformers. Now, at power stations where power are being generated in Kanjidam, for example, the kind of transformer they have there are always step up transformers to to step up the voltages before they are transferred by high tension transmission over long distances. And at the substation, for example, the type of transformers that we have at our various streets are step down transformer because they have to step down. The kind of voltage that are being sent to us from the power stations are too high to be used in household. So that's why we need another type of transformer called step down transformers to be able to step them down. What does it mean to step them down? To reduce the amount of voltage so that it can be used in various households. Now, what distinguishes step up and step down transformer is step up transformer will have more turns in the secondary than in the primary, whereas step down transformer will have more turns in the primary than in the secondary. And there are four main sources of energy loss in a transformer. Number one, energy can be lost through eddy current. The energy loss due to eddy current can be minimized by what? By laminating the iron core. When you laminate the iron core, you create a gap. And because eddy current cannot pass across a gap, that minimizes the energy loss due to eddy current. Number two source of loss of energy in a transformer is what we refer to as hysteresis loss. Hysteresis. Hysteresis loss. Hysteresis loss is minimized by using a soft iron core in the building of that particular transformer. The third source of loss in a transformer is what we refer to as the heat loss or the Joule law. We can minimize heat or energy loss due to heat or Joule loss by using a core of low resistance. And finally, to the question that led us here, we can minimize energy loss due to magnetic flux leakages by making use of efficient core design of that transformer. So if you take a look at the board, that would be the correct option would be option B. Option A, laminating the iron core. That is how to minimize the energy loss due to eddy current. Option B, making the core of soft iron. That is how to minimize energy loss due to hysteresis. Option C, using a coil of low resistance. That is how to minimize the energy loss due to Joule or heat. So the correct answer here is definitely option D. Let's go to the next question. Okay, the number of ejected photoelectrons during photoelectricity depends on that. Now we know there is a particular phenomenon in physics called photoelectricity. At times, it is also called photoelectric effect. It is a phenomenon whereby electrons are ejected from the surface of a suitable metal when light is incident on it. If a light of enough energy called threshold frequency or of enough energy called work function, it will be able to eject electrons from the surface of such a metal, and those ejected electrons are called photoelectrons. And the number of the photoelectrons that are ejected depends on only one condition, and that is the intensity of the light or intensity of the photon. Another question you can encounter here is they could ask you that during photoelectric effect, or during photoelectricity, the kinetic energy of ejected photoelectrons depends on what? It depends on four factors. It depends the energy, the kinetic energy, for those of you that might want to put it down. The kinetic energy of ejected photoelectrons depends on four things. Number one, it depends on the frequency of the light or photon. The kinetic energy of ejected photoelectrons depends on the frequency of the photon. That's number one. Number two, it depends on the color of the light. Number two, it depends on the color of the light. Number three, it depends on the wavelength of the light. It depends on the wavelength of the light. And finally, it depends on the nature of the photocathode. If you don't want to put it that way, it depends on the nature of the material of the photocathode. So these are the four factors upon which the kinetic energy of ejected photoelectrons depends. Once again, the number of ejected photoelectrons only depends on the intensity of the photon or light. But the kinetic energy of the ejected photoelectrons depends on four factors: the frequency of the light or photon, the color of the light or photon, the wavelength of the light or photon, and finally, the nature of the photocathode or the nature of the material of the photocathode. And still talking about photoelectric effect, another area that questions are always common is to ask you that the minimum amount of energy that is required to eject electrons from the surface of a metal during photoelectric emission is called dash. We refer to it as the work function. Whereas the minimum amount of frequency of a photon that can eject electron from the surface of a metal is called threshold wavelength and threshold frequency rather. So please, let's take note of this. Let's go to the next question. Next slide, please. The answer to that is already there. A, intensity of the photon. The next question, please. Okay, which of the following is an evidence in support of particle nature of matter? Now, in physics, there is a particular area called the wave-particle paradox, also called wave-particle duality. Now, wave-particle paradox or wave-particle duality is an idea that light or matter can behave both as a particle and also as a wave, or it talks about the idea that light or matter, don't forget, an example of a matter is electron, can have both particle characteristics and wave-like characteristics. And the particle nature characteristics of electrons are of majorly four types. The particle nature of matter or electron can be supported by evidences such as thermionic emission. For thermionic emission, a process whereby electrons are ejected from the surface of a metal when such a metal is heated. Number two, photoelectric emission or photoelectricity. I just explained that moments ago, so there's no point in wasting time. That's the process whereby electrons are ejected from the surface of a suitable metal when light is incident on it. The third one is Compton effect, and the fourth one is black body radiation. So if you take a look at the board, which of the following is an evidence in support of particle nature of light? What the correct answer be now? All of them. So black body radiation, photoelectricity, Compton effect, all of them are evidences in support of particle nature of light. There are actually four of them, even though three of them are there: black body radiation, Compton effect, photoelectric effect, and the third and the fourth one is thermionic effect. And if you are looking at what are the evidences in support of wave nature of matter, You have diffraction or diffraction, the spreading out of wave around an obstacle. At times, you see diagrams like this, and then you see wave being diffracted like this. That's what we refer to as diffraction, the spreading of wave around an obstacle. Not only that, we have reflection. It's a reflection that brings about echoes, all right? And then we have refraction, we have interference, and so on and so forth. The next slide, please. Okay, which of these is not a non-ohmic, which of these is not a non-ohmic conductor? Now, we have two types of conductors, depending on if they obey Ohm's law or they do not. Now, what is Ohm's law? Ohm's law simply tells us that at constant temperature and pressure, the current passing through a particular metallic conductor is directly proportional to the potential difference. Now, ohmic conductors are those conductors that obey Ohm's law. And what are ohmic conductors? All metals are ohmic conductors. Copper is a metal, it's an ohmic conductor. Silver is a metal. As a matter of fact, silver has the highest conductivity of all metals. Copper is another ohmic conductor, and so on and so forth. Now, what about non-ohmic conductors? Non-ohmic conductors are those conductors that do not obey Ohm's law. And there are several examples of them. All semiconductors are non-ohmic conductors. Glass is a non-ohmic conductor. Thermistor. And by the way, thermistor is a semiconductor that is used in measuring temperature. Thermistor is a non-ohmic conductor. A diode is a non-ohmic conductor. We know a diode is a rectifier. A rectifier is a device that can convert an alternating current to a direct current. The process whereby an AC current is converted to DC is called rectification. A transistor is also another example of a non-ohmic conductor. What is a transistor? A transistor is also a semiconductor that is majorly used as what? As an amplifier and also as a switch. Not only that, we also have electrolytes. Electrolyte, an example is water. Water is an example of a non-ohmic conductor. So you have a lot of them. So based on what I've explained, if you take a look at the board, glass, a non-ohmic conductor, thermistor, from what I've told you, non-ohmic conductor, a diode is a non-ohmic conductor. The correct answer here, that the one that is not a non-ohmic conductor, that is actually an ohmic conductor, is silver. Because I told you, all metals are ohmic conductor, and silver is an example of a metal. We know silver is a transition metal. So that is for that. So the correct answer for that is option B. The next slide, please. Okay, Kirchhoff's law, Kirchhoff's voltage law is a conservation of dash. Now, Kirchhoff was a particular German physicist who contributed immensely to the area of current electricity. He has two laws that are called the Kirchhoff law of voltage and Kirchhoff law of current. Now, the Kirchhoff law of current tells us that the algebraic sum, that's the total, the algebraic sum of all the current at a junction is equal to 0. Once again, Kirchhoff's current law says that the algebraic sum of all the current at a junction is equal to 0. So if this is a junction, and then you have several cables or wires carrying current, this carrying current, this carrying current, this carrying current, this carrying current. The sum of all the current at this particular junction here, according to Kirchhoff's law, is equal to 0. And it is represented by this. When you see this one, that's summation. Summation I is equal to 0. Because there are exam questions like that, they will give you 4 equations like this. They can ask you that which of the following equations illustrate Kirchhoff's law of current. Kirchhoff's law of current tells us that the algebraic sum, that's the middle of the summation, of all current at a junction is equal to 0. And Kirchhoff's law of current is a conservation of charge. Please take note of that. Now, the second law of Kirchhoff is the Kirchhoff's law of voltage. And it tells us, it says that Kirchhoff's law of voltage says that the algebraic sum of all the voltages of potential difference in a closed loop, LOOP, the algebraic sum of all the potential differences in a closed loop is equal to 0. And this Kirchhoff's law of voltage is a conservation of energy. So if you take a look at the board, it says Kirchhoff's voltage law is the conservation of B, which is the energy. That is the correct answer. If the question had been Kirchhoff's current law is the conservation of dash, then the answer would have been charge, because Kirchhoff's current law is the conservation of charge, while Kirchhoff's voltage law is the conservation of energy. Let's go to the next slide. Next slide, please. Okay, which of the following colors has the shortest wavelength? Now we know we have different colors in the visible spectrum: the red, the orange, the yellow, the green, the blue, the indigo, and the violet. We know it is usually referred to as Roy-Green, isn't it? Now the question is asking which of these colors that you are seeing on the board has the shortest wavelength. Now, red has the longest wavelength, while violet has the shortest wavelength. The wavelength of violet is around 380 nanometer to 400 nanometer. So the color that has the shortest wavelength is violet, while the color that has the highest wavelength is red. Please take note of that. Now, if we turn the question around and we're now asking which color has the fastest speed or which color has the lowest speed, red has the fastest speed, violet has the lowest speed. Now, if you turn it around and we're asking for frequency, this time around, violet has the highest frequency, while red has the lowest frequency. So I hope you know the three of them now: the wavelength, the speed, and the frequency. Red has the longest wavelength. Violet has the shortest wavelength. Red has the fastest speed, and violet has the lowest speed. Violet has the highest frequency, while red now has the lowest frequency. And the last thing and the last thing I need to point out now is red is least deviated, while violet is most deviated. You have a question? Okay. What's the question? In another expression of what? Oh, for the second law. Okay. So the mathematical expression for Kirchhoff's voltage law is this: summation V is equal to 0. It's similar to that of the current. Kirchhoff's current law is simply stated that the total, the algebraic sum of all the current at a point is equal to 0. And that is the formula here. Summation of I, that's for current is equal to 0. And Kirchhoff's current law is the conservation of charge, whereas Kirchhoff's voltage law tells us that the algebraic sum of all the voltages or potential differences in a closed loop is equal to 0. And the mathematical representation for that is summation V is equal to 0. And please feel free, if you have questions, feel free to ask them. So that's for that. Just to recap this, violet will have the lowest wavelength. Red has the highest or the longest wavelength. Violet has the lowest speed. Red has the fastest speed. But in terms of frequency, the roles are now reversed. Violet now has the highest frequency, while red has the lowest frequency. And last but not the least, in dispersion, red is least deviated. It suffers the least deviation, whereas violet is most deviated. Yeah? What about the refractive indices for this? Now, somebody is asking about refractive indices. That's the plural of index. By the way, all you have to remember is this: refractive index does not depend on the color of the light. It depends on the nature of the material in which that particular color or that particular light is passing through. Refractive index does not depend on wavelength of a particular color. It doesn't depend on the frequency of a particular color. It depends on the material through which that particular light, maybe white, maybe red, violet, and so on and so forth, is passing through. The next slide, please. The next slide. Okay, in a simple microscope, the image form is that. Now, what is a simple microscope? A simple microscope is also called a magnifying glass. What do we use it for? In biology, we use a magnifying glass or a simple microscope to observe tiny objects or organisms. For example, an amoeba cannot be seen with the naked eye, but we can observe it by using a microscope. A bacterium cannot be observed with the naked eye. It's too small to be seen by the naked eye, but can easily be seen by a microscope. So a simple microscope is a device made up of only one converging or convex lens that is used to produce a magnified image of an object. And in a simple microscope, the object is placed between the focal length and the lens, therefore producing an image with three characteristics. In a simple microscope, the image formed is erect, the image form is visual, the image form is magnified. Once again, the three characteristics of the image formed by a simple microscope is the image formed is erect, the image form is upright, and the image form is visual, and then it is magnified. And if you look at the board, the correct answer here would be option D, visual and upright. So the image form is visual, it is not real. The image form is upright, it is not inverted, and the image form is also magnified. Magnified means that it is bigger than the object. So that's the correct answer. The next one, it says, if the angle of incidence is 30 degrees, what will be the sum of glancing angle and angle of reflection? If I'm talking about glancing angle, we are talking about plane mirror. If you have a plane mirror like this, let me show you this. If you have a plane mirror like this, if this is a plane mirror, and then this is normal, and then you have an incident ray, incident ray like this, striking this mirror here. This is normal. Remember, the angle between the incident ray and the normal, we refer to it as angle of incidence. And then, when the incident ray strikes this, what happens? It will be reflected. So this becomes the reflected ray. And the angle between the reflected ray and the normal is called the angle of reflection. Don't forget, according to laws of reflection, there are two of them. The two laws of reflection says that the incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. The other law of reflection says that the angle of incidence is always equal to the angle of reflection. Now, the angle between the incident ray and the normal is angle of incidence. The angle between the reflected ray and the normal is angle of reflection. But you see this angle here? the angle between the incident ray and the mirror, and the angle between the reflected ray and the mirror, we call them glancing angle. So whenever you are given a question like this, you don't need any calculation. The sum of the glancing angle and the angle of incidence is always equal to 90 degrees. See it for yourself. Here, that's the sum of the glancing angle and also the angle of incidence. So the sum of the angle of incidence and the glancing angle is always equal to 90 degrees. The same thing goes for the sum of the angle of reflection and the glancing angle is also equal to 90 degrees. So the correct answer is 90 degrees. Once again, glancing angle is the angle between the incident ray and the mirror. Also, glancing angle is the angle between the reflected ray and the mirror. And whenever you add the glancing angle and the incident angle together, the angle of incidence, it will always give you 90 degrees. The same goes to the sum of the angle of reflection and glancing angle. The sum of them will always be equal to 90 degrees. The next slide. Okay. If the displacement of an object is 0, its distance traveled is A, 0, B, equal to the displacement, C, greater than 0, and D, impossible to determine. Now, this is a very tricky question, but if you know what displacement means, it's pretty straightforward. The question is saying, if the displacement of an object is 0, its distance traveled is dash. Now, take a look at this. If I move from here to the end of that particular board, I move like this in a straight line to this place, and I get here, and I turn back, and then I move back to where I started from. My displacement is 0. That's the meaning. So when you move in a straight line from point A to point B, and you turn right back from that point B, and you walk back to point A, your displacement is 0. So if displacement is 0, it means that the distance it has covered is what? Is more than 0, because you can't tell me that from here to there is 0. No, whenever displacement is 0, the distance covered is always greater than 0. And please do not confuse the two of them together. Displacement is distance covered in a specified direction. That is why displacement is a vector quantity and distance is a scalar quantity. When you say distance, it only has magnitude, it has no direction. But when you say displacement, it has both magnitude, a particular value, and it has a specified direction. That's why I was pointing to that direction. My displacement is my movement towards this place. Maybe 5 meters towards the north, that displacement. But just 5 meters is a distance. So when the displacement of a body of an object is 0, the distance covered by that particular object is always greater than 0. When you see something like that, you shouldn't bother yourself. When displacement is 0, distance covered is always greater than 0. So the correct answer there is option C. The next slide. Yeah? Yeah? That's right. Okay, so somebody is asking, what if the displacement is greater than 0? The distance covered will still be greater than 0. That's it. The distance covered can never be less than 0. That's a fact. That's understood. You cannot have negative distance. If it's less than 0, it becomes negative. Can you say that you covered a distance of minus 5 meters today? So that is it. So when displacement is equal to 0, distance covered is greater than 0. When displacement is more than 0, distance covered is also greater than 0. Either displacement is 0, distance covered is greater than 0. Either displacement is more than 0 or greater than 0, distance covered is still greater than 0. That's understood now? Okay. The next slide. Okay. So when two vectors are perpendicular, their dot product is dash. Now, when two vectors are perpendicular, now this is the formula. for calculating if you have vectors A and vectors B. The dot product of vector A and vector B. Don't forget, the magnitude of vector A is this. Whenever you see this in physics, it means magnitude of A. When you see this, it means magnitude of B. So the dot product of vectors A and vector B, that's the meaning of dot product, is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. This is the formula for calculating the dot product of two vectors. And if the two vectors are perpendicular, what will be the angle? What will be the value of this particular theta if they are perpendicular? 90 degrees. What's cosine of 90 degrees? And if you use this, if you use 0 to multiply this and this, what do you get? So of course, you can see what the answer is. So whenever two vectors are perpendicular, the dot product of the two vectors will always be 0. But if two vectors are parallel, the dot product of them will be maximum. Because when they are parallel, what will be the angle between them? 0. And what is cosine of 0? 1. That is the highest maximum. That's the maximum or the highest value of cosine that you can ever get. Let me say it again. When two vectors are perpendicular, the dot product of their vectors will be 0. But if two vectors are parallel, which means the angle between them is 0, then the dot product of the two vectors will be maximum. How will they be maximum? Because the cos of 0 here, the maximum value of any angle is 1. And when you find cos of 0, it gives you that maximum value. So the correct answer here is 0. Let's go to the next slide. Okay, so an object is placed 7.5 centimeter in front of a concave mirror. A virtual image 2.5 times the size of the object is observed. Calculate the radius of curvature of the mirror. So let's go to the board to see how we can do this. Okay, and please pay very good attention here. An object is placed 7.5 centimeter in front of a concave mirror. By the way, a concave mirror always has a positive focal length. So we know that the value we are going to get is going to be positive. We know that already. The essence of knowing that is if you do the wrong thing and you are not getting negative answer, you will know that you are wrong, because a concave mirror always has a positive focal length. A convex mirror always has a negative focal length. Just like a virtual image always has a negative image distance, V, while a real image always has a positive image distance, V. So the object distance here is 7.5. So let's put that here. Is equal to 7.5 centimeter. That is the object distance. And we are told that a virtual image 2.5 times the size of the object is observed. What is the meaning of that 2.5 times? It means that the magnification is what? Is 2.5. Because the size of the image compared to the size of the object is called magnification. Don't forget, magnification, that's linear magnification, is V all over U, which can also be image height all over object height. So the magnification is 2.5. That's the meaning of 2.5 times. So here, our magnification is equal to 2. But that's not all. It says a virtual image. When an image is virtual, what will be the value of V negative? That's what I said earlier. Because this is the most important thing there. If you are not careful, if you assign a positive value for V, your answer will be wrong. Let me say this again. For a concave mirror, the focal length is going to be positive. For a convex mirror, the focal length F is going to be negative. For a virtual image, the image distance V is always negative. Always. Every virtual image has a negative image distance V. Every real image will have a positive V. So the image distance now, V, is going to be negative. And by the time you make use of this formula here, magnification, we already know is 2.5, is equal to image distance all over V. If you substitute that, M is 2.5, so it becomes 2.5 is equal to the image distance, that's minus V. And I hope you understand why I'm putting minus V now, because we are told that the image is virtual. All virtual images have negative image distance all over U. And what's our U? That is the object distance. So we can put our 7.5 here. So that's 7.5. By the time we cross multiply, we are left with minus V. Minus V is equal to 2.5 times 7.5. What would that give us? 18.75. That's 18.75. And if we move this minus here, our V now will now be minus 18.75. So now we know our V, we know our U now. To calculate our F will not be difficult. Don't forget, we are looking for radius of curvature. What is the relationship between radius of curvature and the focal length? Radius of curvature is what? Is 2 times the focal length. So when we know the focal length, we just multiply it by 2. And we remember the length formula. 1 all over F is equal to 1 all over V plus 1 all over U. And 1 all over F becomes 1 all over V. Our V is minus 18.75. Minus 18.75 plus 1 all over U. U is 7.5. And then we now say 1 all over F is equal to, we'll find the LCM. The LCM can be 18.75. Minus 18.75 goes in 18.75. That will give us minus 1. Because minus 1 times 1 will give us this. And then plus, how many times? The 7.5 goes here. It's 2.5. And by the time minus 1 plus this will give us 1.5 all over 18.75. But don't forget, that's 1 all over F here. So which means that 1 all over F is equal to 1.5 all over 18.75. What do we do? F now will now be this one going up and this one coming down. That's 18.75 all over 1.5 centimeter. What will that give us? Say that again. Okay, so F now is equal to 12.5 centimeter. But remember, the question is not asking us to calculate the focal length. What are we asked to calculate? The radius of curvature. And what is the relationship between the focal length and radius of curvature? Radius of curvature is what? 2 times the focal length. So what is 2 times? What is that? What is 2 times 12.5? That's going to be 25 centimeters. So you need to be careful because you can see option C is already having the 12.5 centimeter. That is the focal length. That is same to what we are asked to do. The center of curvature is the same thing as the radius of curvature. It is always 2 times the value of the focal length. So we multiply the 12.5 by 2. Yes? Say that again. Can we what? How I got the LCM? Okay. So somebody is asking how I got the LCM to be 18.75. Don't forget, how do we even get this 18.75 in the first place? By multiplying 2.5 and 7.5, isn't it? 2.5 times 7.5. This means 18.75, which means that 7.5 can definitely go in 18.75. That is why we made 18.75 the subject at the SCM. But if you don't know that, all you can simply do is just make the SCM the multiple, the product of the two of them. You can say the SCM is 18.75 times the 7.5. So that 18.75 will go in here, it will remain only 7.5 here. And then the 7.5 goes here, it will remain the 18.75. Is that understood? Okay, so that's for that. So the correct answer for this would be option B. Let's go to the next slide. Okay, it says a cell supply current of 2 ampere and 3 ampere through a 2 ohm and 0.67 ohm resistor respectively. What does that mean? It means that the current of 2A passes through the 2 ohm resistor and the current 3A passes through the 0.67 ohm resistor. The question is now asking us to calculate the internal resistance of the cell. So let's clean this and see how we can tackle this. Okay, so let's look at this. So we have two currents here. So you can make it I1, which is 2 ampere, and it passes through resistor 1, R1. The 2 ampere will pass through which of the two resistors? Is it the 2 ohm or the 0.67 ohm? The 2 ohm. That's 2 ohm. And then the second current, I2, which is 3 ampere, will pass through the resistor R2, which is 0.67 ohms. Now the question is expecting us to calculate the internal resistance of the cell, which is small letter r. We are familiar with this famous equation. Current is equal to the EMF of the cell all over external resistor plus internal resistor. Everybody knows that, I believe. So what we need to do now is, let's cross multiply now, shall we? So 1 times E gives us E is equal to, here we now have current into R plus R. So here, just a moment. The marker soon. So here we have R plus R. So here becomes I times R. Now we have IR plus this times this, that is IR. And this is the formula we need to make this up. Now we have two currents. We just form two simultaneous equations and we equate them. And then we get our answer without any stress. So A here becomes the first current 2 times the first resistor, that's 2 also, plus the first current 2 times internal resistance. So that here we have E is equal to 2 times 2 becomes 4 plus 2R. So make this one equation 1. The second one, E is equal to the second current, that's 3 times the resistor, 0.37, 0.67 plus the second current, that's 3 times then the resistor now, which is R. What 3 times 0.67? Do that again. That's 2.01, then plus 3R. That's equation 2. Now this E, we just equate the two of them. So we equate this one to this. So this becomes 4 plus 2R is equal to, equate it to this. That's 2.01 plus 3R. You can bring this 2.01 here, and we take this 2R to the other side. So this one becomes 4 minus, when this one comes here, 2.01 is equal to the 3R here minus, if 2R goes to the other side, that's 2R. This one will give us 2.21, I think. 1.99. Okay, 1.99 is equal to, this one just give us R. And this particular R now is approximately what? 2 what? 2 ohms. So that's that. You take a look at the board. So that's going to be option A, 2 ohms. Now, if you have a question like this, and you are given 2 currents like this, and 2 external resistors, this is always the go-to formula to you. Just form 2 simultaneous equations like we have done here. Equate them together and find your internal resistance without any stress. So, option A, being the correct answer. The next slide. Okay, what is the final temperature of the mixture of the moisture if 200 grams of water at 80 degrees Celsius is added to 50 grams of cold water at 20 degrees Celsius and well said? So let's look at this. This is under specific heat capacity. And questions here are guaranteed. You can't but always come across this. Now, before I show you how you can do this, let me lay the groundwork first. Look at this. We have 2 types of water here, don't we? We have water at 80 degrees Celsius. That's hot water. And then we have cold water at 20 degrees Celsius. And the two of them are now set together. And we're now asked to calculate the temperature of the mixture. What do you think? The temperature of the mixture is going to be higher than that of the cold water, but it's going to be lesser than that of the hot water. It's just like maybe when you want to run your bath. You woke up in the morning and the environment, the weather was very cold. You don't want to bathe with cold water, and then you just brought out the cold water, and then you eat. You eat some water. That particular water, if you allow it to boil, that's like 100 degrees Celsius. You can't even touch it. You can't even feel it. And you dip your hand in the cold water, it's actually very shiny cold. By the time you add the hot water to it and you mix everything together, what happens? That particular water will not be as cold as it was. It is now higher temperature. And the hot water you added to it will not be as hot as it was now. The temperature will have actually gone down. So the temperature of the mixture is going to be higher than the cold water, but lesser than the hot water. This is what I'm going to do to make it easier to you. So make theta 1 be the temperature of the hot water, which is what? 80 degrees Celsius. And then theta 2 is the temperature of the cold water, which is what? 20 degrees Celsius. And then we now have theta m. That is the temperature of the mixture. Now, don't forget, according to Zeroth law, we know what Zeroth law are, right? Zeroth law tells us that when we mix a hot object, the hot water, for example, with cold water, that the heat will be lost by the hot water to the cold water until the two of them are at thermal equilibrium. What do you mean thermal equilibrium? They're going to have the same temperature. All right? So the hot water will lose heat, while the cold water will gain heat. The heat lost by the hot water will be equal to the heat gained by the cold water. That's assuming no heat is lost to the surrounding. The heat lost by the hot water is going to be, we can say the mass of the hot water. What the mass of the hot water? That's 200 degrees Celsius, 200 gram. And the mass of the cold water is 50 gram. Don't forget, heat lost by the hot water will now be MHC, then theta 1 minus theta M. Please look up. Since the water is hot, heat is going to be lost from it to this. That's why it's going to be theta 1 minus M. Now, heat lost by the cold water, heat gained by the cold water rather, that's MC times C. By the way, you know what C represents? That's the specific heat capacity of water, which of course is not given. The reason why it's not given is they're going to cancel each other out. And then here we now have the temperature of the mixture. Like I told you, it's going to be higher than the temperature of the cold water, which is theta 2. Now that you know this is the heat loss by the hot water, and this is the heat gain by the cold water, all you have to do is equate the two of them. Here, we are now having MH C theta 1 minus theta M is equal to MC, that's the mass of the cold water, C, that's the capacity of water, times theta M minus theta 2. See here, cancel C here. The mass of the hot water is of course 200 into theta 1, that's 80, minus theta M is equal to the mass of the cold water is 50 times theta M, that's what we are looking for, minus theta 2, that's 20 degrees. Now, 50 goes here, 1. What is 50 in 200?
This is 70 centimeter. This is where the object ends. So from air to air now is going to be 20 centimeters. If from air to air is 50, and from air to air is 20, what will be from air to air? That's going to be 30 centimeters. That's everything we need. Then we can now take our moment. We can take the moment about the pivot now. So the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. What do we put? That's 5 grams here. The 5 grams now multiplied by from air to air, which is 30 centimeters, is equal to the m, which we need to calculate, times from air to air, which is 20 centimeters. And the zero here, can cancel the zero here. 5 grams times 3 will give us 15 grams is equal to 2 times m will give us 2m. If you divide both sides by 2, then our mass will be 7.5 grams. As simple as that. So the mass of this particular unknown mass diagram. Okay. Now, a uniform meter rule always has a length of 100 centimeters. That is the of the word uniform. Alright? 100 centimeter or 1 meter. Don't forget, if you convert 100 centimeter to meter, that's going to be 100 divided by 100. 1 meter. So that is why it is from 0 here, certain point, to 100 centimeter here. Is that understood? Now, according to the question, at which point is the 5 gram on?
At the 20 centimeter mark, you don't need to measure it. You just need to just estimate. If this one is the 0 centimeter mark, then around this particular place will be 20 centimeter mark. That is where the 5 gram is on. Is this understood? And then the question goes on and says the meter rule is balanced at the center of gravity. The center of gravity of a meter of a uniform meter rule is at the 50 centimeter mark. Half of it, that is the center of gravity. What is half of length of 100 centimeter? 50. That's where it is balanced horizontally like that. Where the pivot is going to be. Is that understood now? And then it now says with an object of unknown mass m placed at the 70 centimeter mark, if from air to air is 50, then 70 centimeter will be around something here. That's why we put m here. And from air to air is 50. If this one is 70, then from air to air will be 20 centimeter. Well, those of you that you haven't done your mock, that you were able to do your mock yesterday, that maybe about 10 of you, if you are ready, can go to the back now and do it. That's the information. Those of you that weren't able to do your mock yesterday, about 10 of you, if you are ready now to do, you can just go to the back and go and do it. So let's continue. So if the mass m is greater than 7 centimeter, we know from air to air is 50. Then from air to air is 70. So which means air to air will be 20 because the 20 plus 50 that can give us 70. Is that understood? Exactly. And we know that this mass 5 grams is on at the 20 centimeter mark, which means that from air to air is 20 centimeters. Then what is from air to air? Mind you, from air to air is 50. If from air to air is 20, then from air to air definitely will be 30 because it is 30 that you can add to 50 to give you 50. Is that understood? And then you just take the movement at this particular pivot here. That's going to be the vertical force, that 5 grams multiplied by from air to the pivot. That's 30 centimeter. That's what you have here, times the vertical force here, m unknown, which you need to calculate. That's m times from air to air, which is 20. That's what you have here. And then 0 here, or just 10 here, 10 here. Then 5 grams times 3, 15 grams, m times 2, 2m, and then we did the rest. So that's for that. So the correct answer for that will be option A. Now, so and please ensure you go through equilibrium of forces. There is no way you are not going to meet at least one of them, and they are pretty cheap. Because if it requires something like this, once you get your diagram correctly, your answer is going to come out without any stress. So let's go to the next slide, please. The next slide. Okay. But, okay, that's okay. So this next question says a current of 5 ampere flows through a 10 ohm resistor coil for 4 minutes. If all the heat generated is absorbed by 500 grams of water, to how many degrees will the temperature of the water be raised? And you are given the specific capacity of water to be 4,200 joule per kilogram per Kelvin. Now, the person who was asking the question the other time, now you cannot use the 500 grams here. The reason is, if you look at the specific capacity of water, it is given in kilograms. You will have to convert that 500 grams to kilogram. Else, whatever you get will be wrong. So, which means we need to do our conversion here. So let's see how to tackle this. So we are given the current to be 5 ampere I is equal to 5A. We are given a resistor to be 10 ohms and the time to be 4 minutes. Can we use it 4 minutes as it is? We can't. It has to be converted to what? To seconds. What is 4 times 60? That's 4 times 60, everything in seconds. That'd be 240 seconds. Don't forget, heat loss. Heat loss. Heat lost by the coil is going to be H, which is I squared T. Don't forget, there are 3 formulas, if you will, that are used in calculating the heat loss or the heat dissipated in a particular conductor or in a coil. If you are given current, resistance, and time, we make use of this formula I squared RT. If you are given current, the voltage, and the time, what do we use? IVT or VIT. Times, it can be given the voltage, the resistor, and the time. What do we use? V squared T over R. And at times, you can be given just the power, all right, in watt, and the time. What do we use? PT. So these are the these are the 4 of them. So the heat is equal to I squared RT or VIT or V squared T over R, or lastly, we can say that H is equal to PT, where P is the power and T is the time. But here, we are given current I, resistor R, and T time. So that's why we are making use of this. So the heat lost by the coil will be this. And any heat that is lost by the coil will be gained by the water. Heat gained by the water, heat gained by the water is going to be MC, then change in theta. Change in theta. Now, what do we do? According to Zeroth law, each loss is always equal to each gain. So we now have MC theta, MC changing theta, that's the heat gained by the water, is equal to heat loss, I squared RT. What do we need? They're asking us by what degree. So we are looking for our delta theta here. But don't forget, we have been given our M. The mass of water is 500 grams, which will be equal to, like I told you, if you take a look at the unit of the specific capacity of water here, it is given in kilograms. Because of that, you cannot make use of 500 grams. You have to convert it to kilograms. How do we convert from gram to kilogram? We divide by 1,000. So 500 grams divided by 1,000 will give us 0.5 kilograms. Now we are ready to do that. So M now, that's 0.5 times C. That's specific capacity of water. That's 4,200. Then times delta theta is equal to I squared. That's 25 times, that's 10 times T, that's 240. So here, what is 0.5 times 4,200? 2,100, then delta theta is equal to, what is 25 times 10 times 240? 60,000. And then our delta theta now will now be 60,000 divided by 2,100. How will that give us? Say that again. 20. Okay, so 28.57 degrees Celsius. So you can see how easily these questions could be solved. All you need to do is be able to remember those little things. If the units are different, as you can see, the unit of mass of the unit of water being in grams, and the unit of the specific capacity of water being in kilograms. Because of that, you can't make use of that unit of mass in grams. It has to be converted to kilograms, which we have done by dividing by 1,000. And since heat gain must be equal to heat loss, then the heat loss by the heat gain by the water, MC delta theta, is equal to the heat loss by the coil, which is I squared RT, and we equated them, and then we find the value of delta theta, and easily, without stress, we're able to get our answer. The next slide, please. The next slide. Okay, the next slide is on simple machines, and it says a machine has an efficiency of 70%. If the machine is required to overcome a resistance, and by the way, when you see the word resistance, it's talking about load. Load is called resistance. Effort is called force. So when you see the resistance, it's talking about load. Is required to overcome a resistance, that's a load of 40 Newton through a distance of 5 meters using a force, that's the effort of magnitude 30 Newton. What is the distance covered by the effort? And let's look at this. You can do this here. So if you look at this, efficiency is equal to load times distance moved by load moved by load all over the effort times distance moved by effort. Everything multiplied by 100%. If you look at this, we'll be given the efficiency. That's 70%. That's 70 over 100 is equal to, what's the load? That's the resistance. That's 40 Newton. That's 40 times what distance was moved by the load? That's 5 meters there. That's times 5 all over the effort. What's the effort? That's the force of magnitude 30. That's 30 times Then they're asking us, what is the distance moved by the effort? We don't know. Let's say it is x. So here, 0 here, cancel 0 here. 0 here, cancel 0 here. So if you move it here, we now have 7 over 10 is equal to this will give us 20. That's 4 times 5 all over 3x. Now, if you multiply here, 7 times 3x will give us 21x is equal to 10 times 20. We get 3 shares.